everyone. This is the lecture series of hydraulic mechanics subject, and the code of the subject is ME317, unit number first, and lecture number 7. And the topic of for the today topic is manometers. Myself, Rahul Kumar, Assistant Professor of Department of Mechanical Engineering, Suresh Gyan, Vihar University, Jaipur. And today lecture is based on the manometer. And manometer, one question is here arises: what is the manometer? Manometer, this is a one type of device used to measuring the pressure at a point in a fluid. At a point in a fluid by balancing the column of fluid column of the fluid, and some other devices which are used to measure the pressure. These are mechanical gauges, and just like a burden tube pressure gauge, bellows pressure gauge, dead weight pressure gauge, and the diaphragm pressure gauge. These are the different type of devices which are used to measure the pressure of the liquid. For the today's topic, I will cover the manometer concept, introduction, and operation of the manometer. U-tube manometer, measuring pressure with a manometer, multi-fluid manometer, and burden tube. This is the other pressure measuring devices different from the manometer, and the problem related to the these topic, right? Then by the end of this section, you should be able to understand about the manometer, just like a scientific instrument used to measure gas pressure, and understand the difference between gauge pressure, atmospheric pressure, and the absolute pressure, and knows the different ways pressure can be measured, and understand how manometers and burden gauges operates. Understand how manometers and burden gauges operate, right? These are the different type of objective function used in the study of manometers. For the case of manometer is a pressure measurement is vital to any process, and measuring pressure can give you a lot of information about your system. For the measuring the pressure, it gives a lot of information about the systems. In this lecture, we will go over different types of pressures and ways to and how to measure the pressure. And these pressure are three types. One is absolute pressure, atmospheric pressure, and gauge pressure. What is the meaning of absolute pressure? Absolute is a measurement of pressure. Absolute is a measurement of pressure with a perfect vacuum as a reference point. This means that the absolute pressure can never be negative. Means absolute pressure cannot be taken as a negative value. And gauge pressure is a measurement of pressure with the ambient air pressure. Gauge pressure is a measurement of pressure with the ambient air pressure or atmospheric pressure as a reference point. This means that the gauge pressure can be both negative and positive also. But in the case of absolute pressure, this is always positive, right? And atmospheric pressure Atmospheric pressure just like as a pressure at the time of surroundings, right? This is called atmospheric pressure. And the for this purpose, for measurement of this pressure, the manometer are used, which is used to the elevation change of delta Z in a fluid at rest correspond to delta P divided by rho G. Suppose you find the height with the help of manometers, you directly find the elevation height delta Z means the uh, difference in two column of the liquid, and this H gives the delta P by rho G, right? Which suggests that the fluid column can be used as a measure pressure difference. A device based on this principle is called manometer and is commonly used to measure all and small or high and moderate pressure differences, right? High pressure differences. And manometers are different types. Some manometers are simple manometer and some manometer are differential manometer, right? And simple manometer consists of three types of manometer. Another one is U-tube manometer, and last one is single column manometer. Means simple manometer consists of three types of manometers. One is piezometer, U-tube manometer, and single column manometer. In these all types of manometers, piezometer are very simple and it directly give the elevation height. It gives directly give the elevation height delta Z. Then you multiply the two quantity rho and G, and you can get a value of pressure also, right? In U-tube manometer containing one or more fluids such as mercury, water, alcohol, or oil, which creates the difference between the two column. Difference between the two column to keep the size of manometers to a manageable level. Heavy fluids such as mercury are used if large pressure difference are anticipated. Right? These are the three types of manometer. First one is differential manometer. Second one is open end manometer, and third one is sealed end manometer. As you as you can see, open end manometer have one edge connected, one end connected to the one point of this pipe, and another end is open to the atmospheric pressure. So at this point here, this P2 pressure acts as a atmospheric pressure, and this is the internal pressure of the pipe. So just you calculate the difference of elevation. Suppose this is the one line. Just draw here one line, right? Yeah. This is a line shows the datum level of manometer. This line shows the datum level of the manometer, and the difference between these two lines. This is the first line and this is the second line. The difference between these two lines is called the elevation height. This is the elevation height. In the pressure formula, directly given the P equal to rho GH or rho G Z, and this Z shows the elevation or pressure difference between the two columns. Difference between the two columns, right? So this is the and in the case of sealed end manometer, and in the case of sealed end manometer, here one end is closed, one end is closed and another end is connected to the pipe, another end is connected to the pipe. This shows the here vacuum is created, here vacuum is created, and it creates some amount of pressure also. Okay, sorry for disturbance, and then move to the next type of manometer. This is a differential manometer. The differential manometer measure the difference between 2 points of the pipe. Measure the difference between the 2 points of the pipe is here. Here, this is a one pipe. This is a one pipe. In this pipe, two ends are selected. In these two ends, one U tube is connected between them, and this U tube filled by a mercury, and then it creates a here is some pressure and here is some pressure. So it creates a some pressure in the 2 points. In the 2 points, then for these two differences of the pressure, it creates some elevation height here. It creates some elevation height here. Here, this side shows the pressure difference between 2 points. Or we can say that differential manometer gives the direct reading of the pressure difference between the 2 points, right? So this is the differential manometer, right? Okay, then move to the U-tube manometer. Suppose this is a gas chamber. This is a gas chamber. Gas chamber here. How to find the pressure inside this gas chamber? For the finding the pressure, we can use burden pressure gauge, right? First method is burden pressure gauge, and second method is U-tube manometer. So here one manometer are attached here for the purpose of measuring the pressure, right? Then what we'll do here? Here, this is the gray color sign. So the mercury of this liquid, mercury as a liquid, and this is the gas. For this gas, presses this mercury in the downward direction. In the downward direction, and creates a one height difference between the two columns. Between the two columns. Suppose this is the datum level of this manometer is 1 and 2 is here. 1 and 2 is here, and the difference in height, it creates the difference in height just like as a H, right? So consider the manometer that is used to measure the pressure in the tank. Since the gravitational effect of gases are negligible, the pressure anywhere in the tank at the position 1 has the same value. Furthermore, since pressure in a fluid does not vary in the horizontal direction, since the pressure in the fluid does not vary in the horizontal direction within a fluid, the pressure at a point 2 within a fluid, the pressure at a point 2 is the same as the pressure at point 1. Then P2 equal to P1. For this case, you can write here P1 equal P2 equal to P1. But what is the value of P1 is here? P1 is just like this pressure, and the P2 is here, the differential fluid column of the height h. The value of height this h is in static equilibrium and it is open to the atmosphere. Then the pressure at point 2, this point, this point 2, determined directly. This is a P2 equal to P atmosphere plus rho gs. P atmosphere plus rho gs, right? Where rho is the, what is the rho? Rho is the density of the fluid in the tube. Note that the cross-sectional area of the tube has no effect on the differential height h, and thus the pressure exerted by the fluid, is here. However, the diameter of the tube should be large enough. However, the diameter of the tube should be large enough, more than a few millimeter, to ensure that the surface tension effect, and thus the capillary rise is negligible. Means, uh, for this case, we are taking assumption here. Capillary rise is negligible, and the surface tension effect is zero, right? For this case, we are taking the value of P2 is here. P2 equal to P atmosphere plus rho gs. P2 equal to P atmosphere plus rho gs, right? Then move to the, this is a one example. One example based on the measuring pressure with a manometer. Measuring pressure with a manometer. A manometer is used to measure the pressure in a manometer is used to measure a pressure in a tank. The fluid used has a specific gravity of 0.85 and the manometer column height is 55 centimeter as shown in the figure. If the local atmospheric pressure is 96 kilopascal, determine the absolute pressure within the tank. Then find this pressure P. How much pressure? This is a P, and the atmospheric pressure at this condition is here. P atmosphere equal to 96 kilopascal. 96 kilopascal, and the H equal to 55 centimeter. The difference in two levels of the mercury is here. Mercury or any specified liquid, because the specific gravity of this liquid is here 0.85. So this is not a mercury. So the difference in between two levels of this liquid is here 55 centimeter. For these conditions, we can find the pressure inside the tank. For the solution of this question, the fluid in the tank is a gas whose density is much lower than the density of the manometer. Density is much lower than the density of manometer fluid. For the properties, the specific gravity of the manometer fluid is given to be 0.85 and the density of water is here 1000 kg per meter cube. And the density of the fluid is obtained by multiplying its specific gravity. By multiplying its specific gravity by the density of water, which is taken as 1000. Then the specific gravity, then the density of the uh, reference liquid is here rho equal to 0.85 into 1000. This is the 0.85 into 1000. This is a 850 kilogram per meter cube, right? Then the equation P equal P atmosphere plus rho GH. Then the atmospheric pressure is here 96 kilopascal. 96 kilopascal. Then 850 kg per meter cube, 9.81 meter per second, and 0.55 meter. Then 1 Newton 1 kg 1 meter per second and 1 kilopascal divided by 1000 Newton per meter. This is done by creating this pressure in kilopascal only. So the pressure is here 100.6 kilopascal. Note that gauge pressure in the tank is here 4.6 kilopascal, right? Because atmospheric pressure is here 96. So 106 minus 100.6 minus 96, it gives the value of 4.6 kilopascal, right? And the next portion comes to the multifluid manometer, right? Many engineering problems and some manometers involve multiple immiscible fluids of different densities stacked on top of the each other. Means some fluids have a different type of characteristics. Means some fluids are some manometers used one reservoir, use one reservoir, and this reservoir contains different types of fluid. Or you can measure the pressure difference between the two pipelines, and one pipeline flow just like the water, and another pipeline flows a another liquid called the just like a kerosene oil. So you make the difference between two liquids. This is the multi-fluid manometers. And in this slide, such system can be analyzed easily by remembering that the pressure change across a fluid column. The pressure change across a fluid column of height h is delta P equal to rho GH, and pressure increases downward in a given fluid and decreases upward. That is P bottom greater than P top, and 2 points at the rest at the same pressure, right? Suppose for the multi-fluid manometers, this is the fluid 1, this is fluid 2, and this is fluid 3, which the fluid 1 height is here H1, and the fluid 2 height is here H2, and the fluid 3 height is here H3. By the principles of the Pascal's law, we allow us to jump from one fluid column to the next in manometer without worrying about the pressure change, as long as we don't jump over the different fluid and the fluid is at rest, right? Then the pressure at any point can be determined by starting with a point of a known pressure and adding or subtracting rho gs terms as we advance toward the point of interest, just like as a P atmosphere plus rho 1 GH1 plus rho G GH2 plus rho 3 GH3 equal to P1 is here equal to P1. So just like this is a, if you want to find the pressure at the point 1 is here. So this is the atmospheric pressure. Fluid 1 contains the height of H1, fluid 2 contains the height of H2, and fluid 3 is H3. So just right here P atmosphere plus rho 1 GH1. P atmosphere rho 1 GH1 plus rho 2 GH2 and rho 3 GH3 equal to P1. This is the pressure at a point of 1 is here. So this is the concept of multi-fluid manometers, right? And then next manometer is here differential manometer. Next manometer is here differential manometer. Manometer are particularly well suited to measure pressure drops across a horizontal flow section between two specified points due to the pressure of a device such as a valve or heat exchanger or any resistance to flow. This is done by connecting the two legs of the manometer to these 2 points as shown in figure, just point 1 and point 2, and this is the one heavy liquids are present here, and the working fluid can be either a gas or a liquid whose density is rho 1, and the density of the manometer fluid is here rho 2, and the differential fluid height is h here. Then measuring the pressure drop across a flow section or a flow device by a differential manometer. Uh, this is the figure description, right? Then a relationship between just first you make the one datum level. First you make the one datum level, and this datum level here A and B. This is the one datum level, or we can say that this is reference point. Then the setting the result equal to P2 is here, right? P2 equal to P1 plus rho 1G. Rho 1G A plus H. Here the A plus H plus rho 2 GH minus rho 1GA equal to P2. Now that we jump from point horizontally to point B and ignore the part underneath since the pressure at the both point is the same. Simplifying this, P1 minus P2 equal to rho 2 minus rho 1 into G into H is here, right? And then comes to the numerical problem. This is the example number 2, measuring pressure with multi-fluid manometer. Measuring pressure with the multi-fluid manometer. The water in a tank is pressurized by air. and the pressure is measured by a multifluid manometer as shown in figure below. As shown in the figure below, the tank is located on a mountain at the altitude of 1400 meters, where the atmospheric pressure is 85.6 kilopascal. Determine the air pressure in the tank if H1 equal to 0.1, means this H1 is equal to 0.1 meter and this H2 equal to 0.2 meter and this H3 it will become just like as a 0.35 meter. Take the densities of water oil and mercury is to be 1850 kg meter and 13,600 kg per meter cube respectively. Right? This shows the good view of this question is here. Right? Here the height is H1. You can find the pressure at the point 1 also. Here is H1, this is H2, this is H3. So the bottom level of this point is here. Bottom level is here. And this is the bottom level of this. Right. This is the bottom level. This line shows the bottom level of this question. So you can all heights find from this level also. So here is this is rho1g, gh1, rho2g h2, and rho3g h3 is here. For this question, just like as a for the analysis, starting from the pressure at point 1 at the air water interface, moving along the tube by adding subtracting Rogers terms until we reach point 2 and setting the result equal to P atmosphere. Since the tube is open to the atmosphere gives and P1 equal to rho water GH1 plus rho oil GH2 minus rho mercury GH3 equal to P atmosphere. Solving for P1 and substituting P1 equal to P atmosphere minus rho water GH1 minus rho oil GH2 plus rho mercury GH3 equal to P atmosphere plus G rho mercury H3 minus rho water H1 minus rho oil H2 is here. For this case, put the values of all values in this formula. So P atmosphere is here at where is 85.6 kilopascal. The atmosphere is here 85.6 kilopascal. Then 9.81 into 13,600 into 0.35 minus 1000 for this reading 0.1 and for this oil 850 into 0.2. This is here 0.2. This is H2, right? Then the pressure is here 130 kilopascal. Pressure is here 130 kilopascal. And then what is the gauge pressure here? Okay. So what is the gauge pressure? Just like as a 130 minus 85.44.4. The gauge pressure is here 44.4 kilopascal. Right? This is the answer of this question. Then move to the other pressure measuring devices. These are the pressure measuring devices which are directly used to measure the pressure, and this is called the burden tube. Burden tube. And burden gauge are mostly common mechanical device used to measure the pressure, and Brayton gauge is a hollow metal tube that is closed at one end and bent into the C configuration, just like it. C configuration. Here, this is the closed end, and it bent like a C configuration. Or in some cases, it is just like work as a spiral configuration also, right? Some time it is destructive, and sometimes it is helical type of tube, right? The open end is exposed to the fluid. The open end is exposed to the fluid whose pressure is being measured. As the pressure increases, the tube tends to strain the to equalize the pressure in the tube. And this straightening causes gear to turn, which in turn will cause a pointer to rotate into which will inform you on its pressure. Similar like this, just I will give some image of this pressure gauge like this. This end is connected to the this gear. If this is contract, this will show this some deviation in the scale. This shows this some deviation in the scale, right? Suppose when the tube is open to the atmosphere, the tube is undeflected and needle on the dial at this stage is calibrated to read 0. When the fluid inside the tube is pressurized, the tube stretches and moves the needle in proportion to the pressure applied. Proportion to the pressure applied, right? And this is the other pressure measuring devices, button pressure, and the second other pressure measuring devices is barometer. Atmospheric pressure is measured by the device called a barometer. Thus, the atmospheric pressure is often referred to as a barometric pressure, and this is done first time done by the Italian evangelista Torrichini. 1608 to 1647 was the first to conclusively prove that the atmospheric pressure can be measured by inverting a pressure filled tube to a mercury container that is open to the atmosphere as shown in figure. This is the figure. Just here put the mercury, and this is the tube. So how much height gained by the mercury? This is the atmospheric pressure, and the pressure at the point B, and the pressure at the point B is equal to the atmospheric pressure, and the pressure at the point C can be taken to be 0, since there is only mercury vapor above point C, and the pressure is very low relative to P and can be neglected to an excellent approximation. Neglected to an excellent approximation is here, right? This is the, and then one more example is here, measuring atmospheric pressure with a barometer, and determine the this is your question. Then the solution of this question is here. The barometer reading at the location is height as mercury column is given, and the atmospheric pressure can is to be determined for this case. Assumptions: the temperature of the mercury is assumed to be 10 degrees Celsius, and the property is here. Density of this mercury 13,570 kg per meter cube. Then P atmosphere equal to rho gs. Just multiply the rho value, g value, and elevation height, right? Then it gives the value of 98.5 kilopascal. Just this effect should be considered in the exams also, right? This is one more exercise question. Just to note down and solve in your homework. This is question number 2. This is question number 3. And then move to the another question of this lecture is here. MCQ. Right. So these MCQ questions related to the pressure problem. Related to the pressure problem, and in a stationary fluid, how does the local pressure of a fluid vary? Of a fluid is vary. First is with depth only, B in the horizontal direction only, and C both with depth and along horizontal direction, and neither with depth or not to be horizontal direction. But the correct answer for this question is here. Just to think about this, and correct answer for this with depth only, right? A is the correct answer. Which of the following cannot be the value of the absolute pressure of a fluid at any point? Already I have told absolute pressure cannot be reached as a negative value. So this is the right answer for this question. So this is the -1 bar. This is a wrong value for the case of absolute pressure. And then move to the question number 3. A student want to find the absolute pressure of a water at a point below the surface of water. He has a barometer and a manometer pressure gauge. The barometer reads 1.3152 bar, whereas the manometer pressure gauge reads 0.3152 bar. And what is the absolute pressure? Right? This is very good question and very easy question. And the answer of this question is here. But the answer of this, and add these two values, 1.3152 plus 0.3152 equal to, correct answer is here 1.630 bar. This is the correct answer, because manometer always gives the gauge pressure, and this is the barometric pressure, and barometer always gives the atmospheric pressure. So add these two pressure gives the absolute pressure value, right? This pressure always greater than the atmospheric pressure, right? Then the question number 4. In a U-tube manometer, one end is open to the atmosphere, the other end attached to a pressurized gas of gauge pressure 40 kilopascal. The height of the fluid column in the atmospheric side is 60 centimeter, and that on the gas side is 30 centimeter. The manometric fluid used as just like G equal to 9.8 meter per second. Then the what type of liquid are used here? Mercury. This is the right answer, right? Then move to the next question. This is question number 5. In YouTube Mercury manometer, one end is exposed to the atmosphere and the other end is connected to a physiometric pressurized gas. The gauge pressure of the gas is found to be 40 kilopascal. Now we change the manometric fluid to water. The height difference changes by rho mercury equal to 13,600 kg per meter cube and rho of the water 1000 kg per meter. So solve this question and then it gives the correct value. Of this, right? This is the 1260%. This is the correct value, right? And then move to the sixth question. A manometric liquid should suitably have low density, low vapor pressure, low density and high vapor pressure, high density and low vapor pressure, high density and high vapor pressure. But the correct answer for this, the correct answer is high density and low vapor pressure, which is suitable for the manometric liquid. Then question number 7. A simple YouTube manometer can measure negative gas pressure. Yes, this is true. Right? Both ends of YouTube manometer can export to the atmosphere. There exists a possibility that the height difference of the manometer is non-zero. This is true. It creates a both sides same pressure. So pressure difference is not created. Then the question number 9. The below figure shows a inclined YouTube mercury manometer, which is here the pressure is atmospheric pressure is Pg. This is a 50 kilopascal, and here a Pa, and this is H is given in question answer, and this is the 30 degree. So how much this height H is here? So you can find the P equal to rho GH sin theta. Here sin theta equal to 30 degree. So the H value is here 0.75 meter or 0.75 centimeter, right? This is the right value. Move to the next question, and in this question gives here the pressure is Pg, this is the mercury, this is the water, and it creates a difference between two of this H, and the here is pressure is equal to 100 kilopascal. And what is the gas pressure of the gas pressure of the gas? So for the explanation this question, height of the water of the column 0.75 plus 9.45 equal to 10.2 meter, and then the correct answer is here 100 kilopascal. 100 kilopascal is the correct answer for this question, right? And then move to the next section. This is the reference book section. Reference of this lecture is here: Engineering Fluid Mechanics, Rahul Kumar, Fluid Mechanics and Machine, FM White, and Fluid Mechanics and Machine, AK Jain, and Fluid Mechanics, VL Stucker, and Fluid Mechanics with application SK Gupta is here, right? And thank you for this lecture. And I will discuss in the next lecture number 8 about the buoyancy and flotation concept. Buoyancy and flotation concept. Thank you all of you for this lecture.